Hello everyone. So in the second part of these three lectures, so we will talk today about the DC to DC converters. So actually, the we have different types of DC to DC converter. We have isolated DC to DC converter, which actually are formed by power electronic devices and transformers, and we have non-isolated power converter. So we will start with the non-isolated power converter. So as you can see, power converter is a power electronic device that converts from a DC voltage to a different DC voltage level. So it can increase the input voltage or can decrease the input voltage. So if it's increasing the input voltage, it's a buck converter, and if it's increased the input voltage, then it's a boost converter. So the main idea behind DC to DC converter is the chopping of the input signal. So if we have an input, if we have a DC, so if we have a any DC signal, so what the converter is doing, so it's based on the chopping. So if we just switch on, switch off, so what we will do, we actually are switching or chopping the input signal. As we can see, this square wave, the output voltage will be just the average of this signal. So if it's on half of the time, off half of the time, then as we can see, the average voltage will be somewhere in the middle. If we increase the switching on times, then of course the average signal voltage will increase. So we have the output of the DC converter will equal the output regulated current and the output regulated voltage. And of course, because we have using a high frequency for chopping, so we will have some ripple on the output signal. So the output signal, of course, we will have some of this ripple. So this ripple, the RMS of this ripple can be calculated using this formula. And also we will have a ripple in the current, and this will be the ripple. This is the equation for calculating the ripple. And of course, there are two important parameters for the DC converter, which are the ripple factor in the voltage and the ripple factors in the current. So these two will show us how the output voltage is and the output current are regulated. So here we just have a simple chopping circuit, or we have a simple step down DC to DC converter. So as we can see here, the switch is on and switch is off. So when the switch is on, then the voltage source will be connected to the circuit, and a current will go through this resistor. And as we can see that as the on time is increases, then the output voltage across the resistor will increase. And I mean here the average output voltage, because as we can see, the output voltage will be just switching. For this switch, we can use any sort of switches. So we can use BJT, or we can use MOSFETs, or we can use IGBT, or also we can use a thyristor to do the switching of us. So the average output voltage, we can see that the output voltage will equal, we can integrate this signal from 0 up to T. And by the way, T is our switching time, or it's equal 1 over F, where F is our chopping frequency, and usually F is in the range of kilohertz and above. And as we can see here, we can integrate from 0 to up to T1. So from this integration, we can see that the average output voltage will equal T1 over T. or we can say T1F, or what we can identify K. K here is our duty cycle. K is the duty cycle. And the same, we can derive the same formula for the output current. So it will equal VA over R, and as we can see here, the average output voltage will equal K times Vs. So the output current will equal KVS over R. Now, what we can notice here, as the duty cycle increases, it means that the switch will be on most of the time. So as we increase the on time, what we will notice, we notice that the average voltage will increase. So here we can control the output voltage by controlling the duty cycle. If the switch is completely on all the time, so the output voltage here will almost equal the input Vs. So we can achieve a maximum output voltage. And if the switch is completely off, which means that duty cycle is 0, output voltage will equal 0. So as you can see here, we can change the output voltage from 0 up to Vs. So this is what we can see, that it's a step down converter. As we can see now, we have this is the duty cycle, and here we can find the RMS output voltage. So we integrate the we integrate the Vout square, then from 0 up to KT. Then from this integration, we can see that the RMS will equal square root K times Vs. So so the output RMS will depends on Vs, and also it depends on the duty ratio. The same thing, we can find expression for the input power. So the input power will equal the input voltage times the current. So we have the input voltage, or we can say that it's equal VO square over R. And as we can see, the same, we have K in the same expression. So we can see that the input power also, or the power transferred to R, will depends on K. Now we can derive the input resistor. What's the input resistor? It's the resistor that can be seen by the source. So if we connect an ohm meter here, what we can see here, how much the resistor that we can see here. So of course the input resistor will equal this voltage over IA. So because this current here is IA, so the input resistor will equal Vs over IA. And we know Vs, this is Vs, and we know from the previous derivation that the output current will equal KVS over R. So Vs will go then here. We can see that now the input resistor will equal R over K, which means that if the duty cycle is very small, or the switch is off all the time, so the resistor seen from this side would be very high. And this is show you this point. As the duty cycle increases up to say 100%, it means that the switch is on all the time. This means that the source is directly connected to the resistor. So we will get here almost, this will be our R. So here also we can see that the duty cycle modify the voltage, the current, and also it modify the resistor seen by the voltage source. So here, what we can see, that step-down chopper or DC converter acts as a variable resistor load, and it can produce a voltage in the range from 0 to Vs. Also, as we can see that DC converter works at a fixed frequency, but in some application also we can use variable frequency. In our case, it's easier for us to fix the frequency and we change the duty cycle. This makes easier for us to design a filter to get rid of the harmonic, because when our frequency is fixed, then at the output voltage, at the output side, so we will get our signal and we will have some harmonic or some distortion. The frequency of this distortion will be our switching frequency. So this will be our switching frequency. So if we fix this one, then it's easy to design the filter. So say our switching frequency is 25 kilohertz, then it's easy for us to design the filter. So this is what we call about later we need to design a filter to get rid of the harmonics and ripples in our signal. So we get a smoother output voltage. Now there is an important concept that how can we produce a variable duty cycle. So if we have here a sawtooth signal here, and if we have, for example, a DC signal which is my VR, if these are applied to a comparator, so the comparator will be high or low. So say, for example, if VR, in this case, VR is higher than VCR, then the switch will be on. And in this region, the VCR is higher than VR, so the output will be 0. And as we can see, as we increase VR up to VCR, then we can increase the duty cycle, say from 50% to up to 80 or 90%. As VR is getting lower, so the duty cycle will be reduced. So this one. So we define the percent between VCR and VR, or the duty cycle. We define this as the modulation index. So in our case, as we are dealing with baroque tuning, so the frequency of this signal, so it should be in the range of, say, 50 kilohertz and above. So by this means, then we can produce a variable duty cycle to the converter so that we can control the output voltage. Now we will start with a standard DC or step down DC to DC converter. So as we can see here, we have the switch, and what we have done here, we have added a diode, and we have inductor, resistor, and a voltage source. So this part could represent, say, for example, a motor, a DC motor, because we can model a motor as equivalent. The equivalent circuit is just an inductor, resistor, and E can represent the back EMF. Now we can see that this circuit has two modes of operation. So we know that the switch will be on, off, on, off. So we can show that we can have two modes of operation or two circuits. So when the switch is on, so we will have this circuit. So this circuit means that the current will go from the voltage source, and it will go through the inductor, resistor, and the EMF. And as we can see, as we start the voltage source, so what happened here? Because we have to remember that we have two golden rules. The current inside the current through inductor cannot change in 0 time. So the current cannot change in 0 time. And we have another rule regarding the capacitor. So the voltage across the capacitor cannot change in 0 time. And so the rules say that the inductor will try to keep the current, and the capacitor will try to keep the voltage. So the bigger the inductor, the more it will resist change in the current, and the bigger the capacitor, the better its ability to keep the voltage across the terminals. So here, as we can see, we can drive a KVL, or we can use KVL to find the relation, because we are interested to find the parameter of this converter. So if we just apply KVL here, we can see that Vs will equal R times I1 plus the voltage drop across the inductor plus E. So as we can see, we have this differential equation. So we can assume that the initial current here is equal I1 Then we can use Laplace transform to solve this equation, and I will add some notes about how this equation has been derived. So as you can see here, this equation is valid during mode 1. What does it mean? It's valid only when the switch is on. So it's valid from 0 up to kt. And remember, k is your duty cycle, t is your switching time. So t will equal 1 over f. As we can see, we can say that the initial current is I1 and the final current is I2, and then we can prove that from this equation. If t is 0, as we can see, t is 0. So if t is 0, so this part will equal 1, then all this part will equal 0, and this part will equal 1, then yes, I1 of t will equal I1. And as we can see, if t is very long, so we have for example taking very long time, what we can see, this becomes 0 and this becomes 0. So actually the current will equal, after very long time, the current will equal Vs minus E over R. So I mean that this will be after very long time. But what happened here? We will not let the current to increase, because at kT the switch will be off. So the switch will be off. Then what happened? The current will go through the diode, because this circuit is open, and then it will start to discharge through the resistor. So now we go to analyze the circuit in mode. So in mode 2 here, what we can see, we assume that the current starts here at I2, then it will end at some point, what we call here I3. So during mode 2, because the switch here is open, so the current that has been charged by the source will start to circulate in this circuit. So here again, we can write KVL for this circuit. Then using Laplace transform, we can solve for I2. As you can see that this equation is valid from kt up to 1 minus kt. So because kt is the first is the time of the on state or during on, and 1 minus kt will be the time for mode 1. So for example, if k is equal 0.5, then this will be 0.5 t, and this becomes 0.5 t. So it depends on the duty cycle. So now what there is an important concept here. As you can see, the rate of the change of the current here, it depends on the inductor. So if you are using larger inductor, so larger inductor, it means that longer time constant. So it means that the inductor will take longer time to discharge. If we are using very small inductor, then we will have a faster time constant. Then what happened? Then the current can go up to 0. So we should be very careful when we design a converter, because when we choose the inductor to be very small, then the current can be 0. So if current reaches to this 0 point, then what happened? Actually, it will, for example, start to become negative. But what happened here? We have the diode, so the diode will block that. So we will have something like this. Then what happened? Then our converter here is operating in discontinuous mode, because the current becomes 0. So for a proper operation of the converter, so we need the converter to operate in the continuous mode, or the converter to be always in the current always will be positive. Now at steady state, at the end of the off period, we assume that the current will equal I3. It means that under steady state, this will be I1, this will be I2, and this again it will equal I1. So it means that I1 equal I3. So at the end of period 1, this KT, the current will equal I2. The same thing at the end of this period, the current will equal I1. So what you can see here, we have two equations. We have all the variables. K is our duty cycle, T is our switching time, R the resistor of the load, L is the inductance, and we have the voltage source, Vs and E. So as we can see, we have two nonlinear equations. Then we can solve these two equations. So we can see that we have the I1 equation and we have the equation for I2. So from this equation, we can determine how much is our I1 and I2. Now this is, we can see that so we can see that Z actually here, we just for simplification, TR over all we over L, we identify this is as the as Z. Now it's easy for us to find what is the peak ripple current. So peak ripple current will equal I2 minus I1. So we are interested in how much this peak ripple. Then we can just substitute I2 minus I1. So we will get this formula. Now, in order to find the maximum ripple current, so we will take the derivative of this with the duty cycle. So when we take the derivative, then we can get the maximum ripple current. So if we equate this to 0, then we can find that the ripple will be maximum when the duty cycle equal 50%. So if we substitute this back here, so then we see that di max will equal VSR over tangent hyperbolic R over 4FL. And by the way, this is usually very small. So then, because the numerator will be much larger than R, so using this trigonometric identity, so we can see that we can substitute with this to be theta. So then this is which is very important for us. So from here we can see that the maximum ripple in the current for a step down converter is equal Vs over 4FL. So as we have seen before, that if we use a converter with high inductor, then the change in the ripple will be very small. And we can see this as the inductor is becoming bigger, then the ripple will be minimized. And also we can see that if the frequency is very high, what does it mean? If the frequency is very high, then this time becomes shorter. So the time becomes shorter. And again, if the time is shorter, then the inductor will not have enough time to be discharged. So again, this will reduce the ripple in the output current. So now we can see that LR for proper operation will be larger than T. It means that we should select, by the way, L over R is our tau. So it means that if we have the current inside inductor, so it will be like this. So this will be our tau. So this will be our tau. So what we would for a proper design, we should select tau to be much bigger than our switching time. So this is, say for example, this is our switching time T. So here you can see that if this happens, then the current can reach to 0 during one cycle. So what we need to do, we need to select tau to be much more bigger, so that the inductor takes longer time to be discharged. Again, here we can define this time that required for the current to reach to 0. So this is, we can identify, we can find T2. And here from the other equation, we can just substitute the value of T2. Then we can we can identify how much will be T2. Now the most important condition is when the current becomes discontinuous. We can see it from here. The current becomes discontinuous when I1 is equal 0. So we need just to substitute I1 equal to 0, then we can find when this condition happens. So, as if you remember, this is the formula for I1. So if this one is greater than 0, then it's continuous, then or not, or so the border will be when this equals 0. When we solve this, we can see that at this range, or we can identify x, if this condition is happened, then it's continuous. Or at the border, when this is equal, this becomes 0, then the current becomes discontinuous. So from here, we can properly design the converter so that it can operate in the continuous mode. So as we can see, because as we make E bigger, then the converter can operate in this. So now we will investigate the relation for another type of converter, which is as the step up converter. So as you can see here, the switch has been placed in a different way. So, and we have the inductor. It's in series with the voltage source. And here we can see also the diode place has been changed. Now, as we can see here, when the switch is on, all the voltage source will be across the inductor. So the inductor will be charged. During the off or when the switch is off, so the current will go from the V source up to the load, and also we can see that the inductor also will discharge in the load. So we can see that the voltage across the load will equal the voltage across the inductor and the voltage source, and it clearly shows that the voltage here will be higher than the input voltage. So this is why we have this step up converter. So as we can see here, the current in the inductor during switch on will start to increase, and here at this point the switch is off, so the inductor will discharge through the load. Now we can see that we know that the voltage across the inductor is given by this equation, or we can see that the I will equal during the on, because VL will equal just Vs, and the time here dt will equal T1. So then this is give us the change in the current, and the output voltage will equal Vs plus VL. So this will be our VL, because VL will equal LDI over T2, because this happens when this happens during the off time. And if we substitute with DI here, then we can get this relation. And as we know that T1 will equal KT, and T2 will equal 1 minus KT. So from this we can do some simplification, and as we can see, the output voltage will be Vs 1 minus K, and it's clearly this formula shows that this will be a Bose converter, because if K say is very small or is around say 0.1, then this will equal 1 over 0.9, which is actually amplification, but not too much. If K is almost 0.1, if K is equal say if K is equal 0.9 somewhere here, so this becomes 1 over 0.1, or it's equal 10. It means that the output voltage will be 10 times higher than the input voltage. So now we can do the same analysis that we have done with the buck converter. So we have this mode 1 the switch is on, so the voltage source will be across the inductor, and the diode here will be reverse bias. And also we have the during the off state, so we will have the voltage source and the inductor. So this is the relation uh, in the first mode, or the on mode, and it's easy. We can easily integrate this to find I1. And as we can see, I1, it has initial condition, or it's at T0 it's equal I1, and at T equal KT it will equal I2. And this condition should be satisfied, because the inductor will start to rise there, and the voltage of course should be positive, so that the diode will be forward biased. During mode 2, so we have the Vs and also we have Ve. So Vs will equal the voltage across the inductor plus the plus Ee, and from this one we just integrate to get I2. And as we can see, the initial condition for this at when t is equal say 0, it should equal I2. At the end of this period, of course, it should be equal I1. And here, if these conditions are satisfied, the inductor continue. If this condition is not satisfied, then the inductor current continues to rise, because this is what happened, that in each time, if the inductor is current is increased, but there is not enough time to discharge this energy, then every cycle the inductor current will just increase. So now we will just add some resistor to the buck converter. So here we added a resistor. Then we just need to do the analysis again. So here we have mode 1 when the switch is on, and we have mode 2 when the switch is off. So we have this complete circuit, and for simplification here we just neglected the voltage across the diode. So during mode 1, so we have this Vs will equal the voltage drop across the inductor, so we can just integrate the circuit to get to integrate this equation to get I1. And remember, this will be valid in the range from 0 up to KT, so it means it's valid in this range, and it starts at I1 and at I2. And again, during mode 2, so we will have Vs and we have E and R. So Vs will equal R times I2 LdI over dt plus E. And again here we should use Laplace transform, then we can get the expression for I2. And again, I2, the initial condition for I2, it will equal I2. And at the end of this period, it should equal I1. So we will do the same. So we have two equations. Then we can solve them for I1. So we have this equation for I1, and we have a equation for I2. So yeah, sorry, I'm talking about this one. And again, we can solve this two equation to get expression for I1, and we can get expression for I2. And by the way, if we know how much is the duty cycle and we know all the parameter, then we can calculate how much is I1 and how much is I2. And it's clear that it's easy for us now to find the ripple. The ripple will be equal just I2 minus I1. And to remember that this is valid if the E is less than the voltage source, because what happened if this, say we have this diode and we have the inductor and the voltage source. So what happened if E is greater than Vs, this diode will be blocked, so the current cannot go, and of course the converter will be operating in the discontinuous conduction mode. So now we can see what actually the most important parameter or limiting parameter for the frequency. We can see that we can control the duty cycle between K minimum and maximum. So it means that if you have a converter, then say for example you can change your K between K minimum and K maximum. And this is definitely for real switch, they will not be 0 and 1 or 0 and 100%. So usually they become, for example, larger than 0, say 10% from to up 90%. This is because of the non-linearity in the converter. So it would be, say, for example, from 10% up to 90%. And again, we can see that the ripple current will depends on the chopping frequency. The higher our frequency, the less will be the ripple. And also, the frequency should be as high as possible. So if we choose the frequency to be very high, then of course we are reducing the ripple current. And also, it's very important because when we are working with high frequency, then when we design a filter, the size of the filter components, which are the inductor and the capacitor, will be less than if the frequency is lower. So then here we can minimize the size of the filter. But on the other hand, increasing the frequency will increase the switching losses in the switches. So what actually the most important thing that we have the ripple current, we have the maximum switching frequency, we have to satisfy the condition for continuous operation, and also the minimum value for the inductor to achieve this. And also it's very important that we minimize the total harmonic. Now we have seen that how the DC converter, the two types, the buck converter and boost converter works, but actually we have investigated them during the open loop operation. Usually they are in this structure, so we have some sort of feedback. So we have this input voltage and we have the output voltage. So here we measure the output voltage, then we have our reference, say that we need to design a converter that has a fixed voltage of 5 volts. So whatever is your load, so you have a variable load, then you need to make sure, because when the load is changing, of course the output voltage will change. So this we do not want this to happen. So here, if we choose the reference, say for example 5 volt, then we can use this feedback signal, and then we can use, for example, BID controller. Then here we can manipulate, or we can play with the duty cycle. So as the load change here, the output voltage will be almost equal 5 volt. So this is actually what we have in the switching mode regulators. So here we can do any conversion, and also we can regulate if our input voltage is not so regulated by the proper choice of CNR. And remember that to maximize the efficiency of the regulator, the minimum oscillator period should be about 100 times longer than the transistor switching time. So say for example, if the transistor has a switching time of 0.5 microsecond, then the oscillator should be around 50 microseconds, which means that we give enough time for the switching of the transistor. So here we can see that we have a buck regulator. So we have the same structure for the converter, but here we just added a sensor to measure the voltage, and we have our reference. Then we have the compensator, or we have the PID controller. Then here we have the pulse width modulator. Then when this will be sent to the driving to the gate, or to the drive circuit of the switch, so it can be on and off. Now we can see that these the MOSFETs, or the switch and the diode, we can see them as two single pole, single throw bidirectional switch, which is mean that if the switch is on, then we can say that it's S1 during N. So this is can represent these two two devices together. And if the switch is off, then the switch will be here. So again, we have these two mode of operation. So now I think now it becomes straightforward. Then now we can just do the analysis into two modes. Now we just need to investigate the waveform of the currents and the voltages. As you can see here, when the voltage is when the switch is on, so this is will be the switching voltage, and as we can see, the current in the inductor will start from I1, I2, and again it will have a ripple. Now we have added a capacitor. So what the capacitor will do? The capacitor will keep the voltage across the resistor almost constant. So it means that the voltage across the resistor will be constant, and also the current will be IA will be almost constant, as we can see here. So here we can see that we have the waveform for IL, this is IL, and we have the waveform for IA. So then we can find the waveform for IC. So it just will equal using KCL, then Kirchhoff current law. So this will be IL minus IA. So this will be our capacitor current. So what you can see here, the capacitor current is sometimes positive and negative, which means that the capacitor will be charged during a period of time, then it becomes discharged. So we will have this ripple in our output voltage. And also we have here the source current. As we can see, the source current, it starts to increase when the switch is on until it reaches some peak. Then what happened here? The switch is off. So when the switch is off, so the current goes to zero. So here we can see this is the different waveform. So now we will again do the same sort of analysis. So here we have the voltage across the inductor, and as we know that during mode 1, so we have Vs and Va, because the switch is actually is connecting the source to our circuit. It's to our circuit, and we have its the load Vr. So it has the it will be connected to the circuit, and here with the capacitor. So Vs minus Va is the voltage across the resistor, so it will equal LdI over dt, or we can say that's equal LdI over T1. So from this one we can find the period T1. During period 2, what happened during period 2? So the switch is on, so Va will equal the voltage across the inductor. Okay, because we have only the inductor in the circuit, the inductor, the capacitor, and the resistor. And again, from here we can find D2. The interesting thing here that we have now two expression for Di. So Di will equal, from this equation, Di equal T1 times Vs minus A over L, and also from the equation in mode 2, Di is equal this one. So if we just do some calculate some derivation for this one, then it's very easy for us to find that Va will equal KVS and Is will equal KIA. So it's clear that our converter is a buck converter. Now we turn our attention to find the ripple in the current. As we can see that the total time will equal 1 over F, or would equal T1 plus T2. So we can just add T1 and we can add T2. So if we add this together and we do some simplification to the Di expression, then we can reach to this one, these two equations. So actually to design your converter, this is actually the most important thing for you. So from here you can see that the ripple current will depend on the duty cycle, it depends on your source voltage, it depends on the frequency and the inductor. So from here you can calculate the ripple in the current, and also you can use this expression as you will do in the assignments. Then from this expression you can design the converter. So for example, to design the converter to have, say for example, if your design that require that you have 0.1 amp ripple, then you can work out this parameter so that you can achieve this ripple. Now, another important parameter is the ripple in the voltage. So we know that the inductor current will equal the current in the capacitor plus the output current. So we will just take half of this period, and the current in the capacitor can be approximated with this equation. So we know that the voltage across the capacitor will be just the integration of the current. So if we integrate from 0 up to t, and we assume that the initial condition is 0, so if when we integrate this one, then we can find that the voltage will equal this. So it's very interesting to see that the ripple in the voltage equal the ripple in the current over 8 times the frequency times the capacitor. So here we can substitute from the previous equation, the previous slide, then we can reach to this equation. So for what we can see here from this equation, you can design your converter. I mean to design the converter to find the capacitor that give you the predetermined voltage ripple. So in the equation in the previous slide, you can design the inductor for a given ripple. And here, after you design your inductor, you can design the capacitor that give you the required ripple. Now we go to the last two design requirement. So our design requirement is to find what's actually the condition that makes the converter works in continuous operating mode. So if we assume this is our, by the way, this is our ripple in the current. So we assume that it will be 2IL or 2IA. What does it mean? It means that when the ripple is maximum. The ripple is maximum when I1 is 0. And this will be I2. And I average will be just in the middle of them. So if this happens, then this will be the average current 2IA. And we know from the previous equation that IA will equal KVS over R. So if we just do some simplification to get L, so then we can find that L will equal this equation. This one is the critical inductance. What does it mean? If the inductor is below this value, then what happens? The inductor current becomes less than 0, or the converter will work in discontinuous mode. So for a continuous mode operation, your L should be greater than LC. Again, the same thing, we do it for this equation to find the maximum, to find the condition for continuous mode for the capacitor. So again, we assume that 2VA, that this is the maximum ripple. Then from this equation, we can find the critical capacitor. So if the capacitor is less than, if the capacitance is less than this CC, then your converter will be operating into discontinuous mode. Now we just our previous calculation to the boost converter. So as we know that we have the boost regulator, so we have the switch, we have the capacitor, and we have the load, and we have the inductor. And again, we have two modes of operation. So when the switch is on, so we have this circuit, and we have the mode 2 when the switch is off, so we have this complete circuit. So then we just need to analyze the circuit in the on state and the off state. Then we can derive the expression for the ripple current and the ripple in the voltage and the limiting value for the inductor and the limiting value for the so during the on state, so we will have the voltage will be the whole voltage will be across the inductor. So This will be di over dt. So the same thing, we find it for t1, and in this case we find it for t2 during the on state and the off state. So here from this one, we know we are interested in that to find the ripple. So the ripple actually is equal I2 minus I1, and we can see here that the ripple, we have two equations from T1 and T2. So if we make this two equations equal, because we know that for the on state and off state, of course, the ripple will be the same. So if we just substitute with T1 and T2, then we can see that actually the relation between the output voltage VA and the source voltage is actually a relation for a boost converter. So actually our converter is a boost converter. Now, again, we can also derive the equation for the relation between the source current and the output current. Now we turn our attention to find the ripple in the current, as we have done with the buck converter. So the total switching time will equal T1 plus T2. Then we can substitute the expression for T1, and here the expression of T2. Then we do some simplification. Then here we can find that this is from here. We can find the ripple current for the boost regulator, or so we can either use this equation or this equation. And as I have said before, we can use this for calculation, or also we can use them to design the converter. And again, here we have the equation for the voltage across the capacitor, and in this case IC will almost equal IA. Then here we can just do the integration. Then we can find we substitute with the T1, because here we integrate from 0 to T1. Then we can end up with these two equations. So from this we can use this either this. Just this one is just simplified version of this equation. So from here you can compute the ripple in your voltage. You can compute the ripple in your voltage, or if you know the how much you need the ripple to be, then you can use this equation to find how much the capacitor should be, so that it can give you the proper voltage ripple. And again here we use the ripple current here equation to find what is the limiting inductor value. So if we solve this, then we can determine the minimum required inductor. And the same here, we have the expression for the voltage, then we can find the minimum required capacitance. So this, we will design them to make sure that our regulator will be working in continuous operating mode. So now we are done with the buck regulator and boost converter, and also a boost regulator, and at the end of the lecture also we will talk about the buck boost regulator. Before that, we want to see how it looks like in real life. So actually we have the AC source from the power supply, say 20 to 20 volt. Then before we can apply the AC signal to the converter, so we need to do a rectification. So actually here we have a rectifier. So this one, it shows you that this is your input signal at this one. So at this point here, your signal will be, say, almost something like this, DC. Then here, if you use buck or boost converter, then you can say, for example, you can increase or you can decrease the output voltage. So you can see this is a non-isolated converter, because we do not use any transformer. And be careful that this configuration is valid if the DC voltage level is close to your AC voltage. So say, for example, if it's your voltage is 48 or 92, so you need a high DC voltage, and because this will be 230, so it should be somewhere close, because it will be difficult if this voltage is 220 and then our output is just 5 volt. And we will see later that how we can achieve low voltage with high input voltage. Another way to do it, if we have a three-phase rectifier, and then we have a, say for example here we have a boost converter. So here if we have a three-phase, then we can rectify this three-phase, then we can do the conversion. So here we have AC to DC conversion, then we have DC to DC conversion. Okay, before the last part, so when we want to regulate DC converters, we need to design the controller. To design a controller, we need to find the transfer function of the what does it mean? I have this converter, but actually what I'm looking for as a control as a control designer, you need to find the expression for your converter. So we need a G of S, or it means I need to convert this converter to its domain, or to find a transfer function, for example, so that I can use, say for example, feedback. Say this is my V reference and this is V output. Then you can say, for example, design BID controller, so that you control the regulator. So actually, how we can drive a transfer function or for the converter. So the easiest way is that to assume that the converter operates in two modes. We have the on mode and we have the off mode. So we can see that the on mode is the switch is on, and during the off mode the switch is off, so we do not have the power supply. And then what we need to do, we need to specify something that we call them states. So how we can select the state? As a rule, any current during the inductor can be selected as state. This will be the current. So my first state will be the current in the inductor. Why we use this as our state variable? Because we know that the current throughout the inductor will not change in zero time. And again, we will select any voltage across the capacitor to be our state variable. And here we can see that we select the voltage across the capacitor to be our second state, because we know that this voltage will not change in zero time. So from x1 and x2, we can identify any other variable in our circuits. So during mode 1, we can write KVL. As you can see, KVL, we assume that the input source is equal U1. So U1 will equal the voltage across the inductor. How much the voltage is across the inductor? It's actually equal L di over dt. But now you can see that we select I to be my x1, so it will equal L x1 dot. Yeah, as you can see here, plus the voltage across the capacitor. The voltage across the capacitor, we have said that it's equal x2. So this is for mode this is for the first equation. And also so the first equation we get it from applying KVL across through in this loop. And because we have two variables, so we need two equations. So the second equation we can get it from applying the KCL. So we see the current here, the current here, and the current here. So as we can see here, the current in the capacitor will equal C dV over dt. Now, what's your V? V is actually x2. So the current in the capacitor will equal C x2 dot. So can you see Cx dot will equal x1, the current in the inductor, minus x2 over R, because what is the current in the resistor is actually the voltage over R, but we have specified that the voltage will be x2, so it's equal minus x2 over R. So what we can see here, we can rearrange these two differential equation to make x1 dot here and x2 dot here. Okay, so now we have we have two equations for the converter circuit in the. Now we can make some arrangement, and please check, we have some mistake here. So this should be plus and this should be minus. So here we can write these two equations in state variable form. So x dot, it means that x dot will equal, this is my state variable, so my state variable x dot will equal x1 dot x2 dot. So here we can see that we convert this to this formula. So a1 will equal, is given by this one, and b1 is equal by this one. So here we have put these two equations into a more compact form. So now we find the equation for the converter during the off state. So the off state, the only difference, as you can see, that the voltage source does not exist because the switch is on. So we do the same thing. So we have these two equations. Then we can recall the new state in the on, or we distinguish them in the off state by writing 2. So 2, it means during the off state. So we have the same matrix A, we have the same state variable, but here our source vector is equal 0. So now we have two equations, or we have two models, one in the on state and one in. Then we can combine them together. We know that this is the converter model in the on state, and this is the converter model in the off state. So on state we multiply by k, off state we multiply 1 minus k. So we just do this multiplication, then we can find the final final equation. So what we can see here, we can see that here the x1 dot, which is means the current in the inductor, x2 dot is the voltage across the capacitor. So they are depends on this equation. So we can see that actually they are depending on u1 or u1k. As you can see, this is my input. My input is actually k u1, or I can say that it's equal k vs. So I will show you in a separate explanation how we can convert this to a transfer function, how we can convert the state model to a transfer function, so that you can design, for example, a BID controller to your converter.